All right, here's our recording for tomorrow. So as you prepare for class tomorrow, note that we will finish the slides that we began on Monday, and we will also go through the latter part of Chapter 9, which is really focusing on why are complex diseases so hard to figure out genetically and so hard to treat, and what are some hypotheses as to why complex diseases are increasing in prevalence in developed countries. So some key terms. First one, common disease, common variant, and this describes many of our common genetic diseases and basically describes that the reason they are common is because there are very common mutations that correlate with them. Several common mutations can all contribute to an increased genetic likelihood to develop the disease, but all of these variants have very small effects. But because they're common, because they are common mutations, it's very easy to be in a situation where you end up with several of them. And so even though the effects of each one of those mutations is very weak, the cumulative effect of those mutations is enough to give you a genetic predisposition towards developing the genetic illness. Common disease rare variant. This describes other common diseases in which you the mutations that give you a genetic predisposition towards this illness are rare, but when they're there, it has a very strong effect, and so it makes it very likely that you will develop that genetic illness. And then if you have several loci with rare variants, even though the probability of any single mutation may be low, if there are several different loci with rare variants, then you have a greater probability of actually having it. For instance, let's say you have a 1 in 20 probability of passing on some mutation to your offspring. That's a fairly low probability. That's much higher than some of these variants that we're talking about, but that's still fairly low. But if you have 10 children, now you're talking about that there's a lot of opportunity for that rare event to happen. Same thing with these rare variants. Each individual mutation at each individual locus might be rare, but if you've got hundreds of loci, now you can have a pretty decent probability of getting one of these rare variants with their strong effect and having a large genetic predisposition for developing this genetic illness. Synthetic associations. So this is something that happens with these rare variants where they will basically piggyback on some of the more common variants. And so what we find is with some of these mutations that happen very rarely, they correlate significantly with other common variants. So while they might be rare in the entire population, oftentimes they're very not very common, but they're more common in certain groups that have a common variant present in that family. Stochastic fluctuations. This term is a description for why these complex diseases are so challenging, and it's because the genetic programming it's somewhat random as far as what the impact on the phenotype is going to be. And so it's the idea that even from the same genome with the same environment, you can still get variation in the expression. And we see this clearly in identical twins. Identical twins that maybe even share a placenta and definitely share the same uterus. And so they have the most significant aspect of their environment shared. They're genetically identical, at least at the very beginning of development. And then they grow up together and they experience very similar environments, and yet they're different. They have some different expressions, and some of that is going to be because, there are some genomic differences, but some of that is also from these stochastic fluctuations that you have, various phenotypes that show up from the same genotype because of differences in gene expression, these stochastic fluctuations. Bonferroni correction. Bonferroni correction is basically a statistical tool that is trying to deal with the problem of having a lot of samples, a lot of different samples. So let's say you're trying to figure out, does this particular region of the genome correlate significantly with this genetic illness? And most of our statistical tools, we set our if we set our p or our alpha at 0.05, and so if it's less than 0.05, our p-value is less than 0.05, less than that alpha level, we say, okay, well, there's less than a 1 in 20 chance that these differences could happen if the two sample groups are actually the same. So let's put this in context. Let's say we're comparing individuals without a particular variant, without a particular mutation, with individuals with a mutation. And we basically get to a probability of the prevalence of the genetic illness being different in your samples. If the probability of that is less than 5% or less than 0.05, we tend to say, okay, there's significant statistical evidence that these two groups are legitimately different. That the group with the mutation develops this genetic illness significantly more often than the group without this genetic mutation. Okay, and we tend to, again, we set that alpha level at 0.05. What that means is our probability of making a mistake and actually saying the two groups are different when they're actually not different is 5%. So we have a 5% chance of making an error in which we say there is a difference, even though there isn't one. And so you're like, okay, well, 5%, that's not that big of a deal. But now if we're trying to do this with 100 different loci or 100,000 different loci, and we're saying, okay, well, each one of those has a 5% probability we have a 5% chance of making a mistake and saying there's a difference, or that mutation, a mutation of that locus correlates with this genetic illness. Well, now you have 100,000 different loci. Now you're talking about a lot of error unless you do what's called a Bonferroni correction. And so a Bonferroni correction, you reduce that, the alpha to a value that's equal to your alpha 0.05 divided by your number of different tests. So in this case, 100,000 different loci. Now, what that does is it eliminates the probability of making an error, but it also increases the probability of making the other kind of error, and that's assuming the two groups are the same when they're actually different. So we'll talk more about this on Wednesday. The thrifty gene hypothesis. So now we're getting into potential explanations for why certain complex diseases are increasing in prevalence. The thrifty gene hypothesis basically says that there are certain variants in the human genome that are the result of us basically being designed to live in a hunter-gatherer society, in which we have to be able to endure periods of famine, periods of starvation. And so we have these variants that basically make us well equipped to be able to handle prolonged periods of starvation. And then now in a developed society where we don't experience those periods of starvation, we end up being able to put on weight very, very quickly. And so this is an explanation for why obesity and heart disease and some of these other complex diseases, type 2 diabetes, this is an explanation for why these are more prevalent in developed nations. And that's because, again, we have these variants that make it very easy for us to put on fat to be able to, hold us over during periods of starvation. But when we aren't experiencing those periods of starvation, actually lead to higher rates of obesity, higher rates of heart disease, higher rates of type 2 diabetes. the old friends hypothesis. So this is a subset of what's called the hygiene hypothesis, and it's basically an explanation for why certain autoimmune diseases and other complex genetic illnesses are more common in developed countries. And it's the idea that our immune system basically evolved alongside certain pathogens. That I mean, you could look at it as far as like humans were designed to live among these specific pathogens and to actually experience exposure to those at an early stage in life, and that those are really necessary to train your immune system properly. And so when you don't get to spend time with those old friends, your immune system does not develop properly, and so you end up with you know, being significantly more likely to develop issues where your immune system reacts to things that are not dangerous at all, or even reacts to self. Antagonistic pleiotropy. So pleiotropy, again, this is a term we haven't seen in a little while, but it's the phenomenon in which a single genotype influences several different phenotypes. And so antagonistic pleiotropy is a description of why these complex diseases tend to show up late in life, in that maybe the variant is really helpful early in life. Whatever that genetic mutation is, it's really helpful early in life, maybe in development or when your body's still maturing. But then late in life, it becomes, it triggers certain phenotypic changes that result in this genetic illness. Again, this antagonistic pleiotropy. And so, yeah, it's a potential explanation for, one, why do these variants even exist? Why doesn't natural selection eliminate them? Well, maybe they're helpful early in our lives in development, and then they become, you know, harmful late in life when we're already post-reproductive, and so there's no ability for natural selection to eliminate them. And in fact, natural selection favors them because they encourage and facilitate proper development. All right, so again, as you prepare for class on Wednesday, make sure you watch this video. Make sure you prepare to go through these topics in more detail and to finish up our section from Monday.